Okie dokie. Are we rolling? Okay, hello everyone, and welcome to our lesson on Earth Science. Today we are doing Chapter 8. Our lesson is on earthquakes and the Earth's interior. Before we get started, I think we should review some of the things that we talked about in Chapter 5. Remember, in Chapter 5, we started to talk about this idea of plate tectonics. And we learned a couple of important things there. Remember, we learned that the Earth's surface is actually made of these large plates of solid rock that we call the lithosphere. And we learned that these plates of rock are actually almost like rafts floating on a sea. And the sea is this large area of liquid rock inside the Earth, which we call the asthenosphere. Now, the other thing we learned is that it's important to remember that much of this is theory. The fact is, we really don't know that much about the inside of the Earth. We actually know more as scientists. We know more about faraway galaxies than we know about the center of our own planet. And I know that sounds fantastic. It sounds unbelievable, but it's true. We can use telescopes to look at faraway galaxies, but we don't have a telescope that can look into the center of the Earth. And it's still impossible for us to actually drill all the way into the center of the Earth. The Earth is just too big for that. So keep in mind that much of this is unknown, much of it is theory, but with that in mind, let's jump into 8.1 earthquakes. First, we're going to look at what is an earthquake. Well, an earthquake is the vibration of Earth produced by the rapid release of energy. We're going to talk a little bit about why an earthquake is such a rapid release. We are also going to look at these concepts of focus and epicenter. Both of those are illustrated on slide 4. If you want to look on slide 4 of the presentation, you can see the focus is the point within the Earth where the earthquake starts. That's that red dot deep down in the Earth with all of the green arrows coming out. The epicenter is the location on Earth's surface directly above the focus. All right? And the other term we're going to look at today, fault. Those are the fractures in the Earth where the movement has occurred. Remember what we learned in our lesson about plate tectonics? We learned about different types of fault lines. We learned that these plates in the lithosphere are always moving around very, very slowly. And we learned about 3 different types of faults. Remember, we learned about divergent boundaries, where the plates are moving apart. And we saw this is taking place in the Atlantic Ocean, in what we call the mid-Atlantic range. And we saw this taking place in East Africa, in what's called the Great Rift Valley. Places where the Earth's crust, 2 plates are being pulled apart, and new magma is coming up to replace that old land, or to fill in that space between the 2 plates. We also learned about, let's see, subduction zones or convergent faults where two plates are meeting each other. And when this happens, we get subduction, where one plate actually moves over the other. And when we learned this, I told you to think about our weather fronts from our lesson on weather. We learned how in a cold front, cold air will actually push the warm air up. We'll actually move into an area and displace that warm air, push it up. Well, we learned in the last lesson that the same thing happens with these tectonic plates. One plate will move in and it will push the other plate up. We saw this is what's happening in the Himalayas, where the Indian plate is running into the Asian plate and it's pushing that land up, and that's what's creating the Himalayan mountains. The other type of fault that we saw is called a transverse fault. That was like our occluded front from the lesson on weather. That's where two plates are moving in opposite directions like this. And we saw that's what's happening in places like California, where with the San Andreas fault, where two plates, the Pacific plate and the North American plate, are rubbing one another like this and creating a lot of earthquakes. This picture on slide 4, it kind of looks to me like a subduction zone. It looks like it looks like what we learned about in India, with the Himalayan mountains being pushed up. On slide 5, we see an example of slippage. This looks like an example of a transverse fault, where you can see how those two plates have moved like this. There's not one plate pushing the other one down. There's not one plate pushing the other one up. They're just moving against one another, creating that line going across the middle of the picture. So what causes earthquakes? On slide 6, we see the elastic rebound hypothesis. That is actually illustrated on slide 7. You can see that illustrated with the good analogy of breaking a stick. Here, most earthquakes are produced by the rapid release of elastic energy stored in rock that has been subjected to great forces. When the strength of the rock is exceeded, it suddenly breaks, causing the vibrations of an earthquake. On slide 7, think about breaking a stick of wood. If you break a stick, it doesn't break instantly. First, it's going to bend. It's going to bend a little bit more. It's going to start to crack, and then, boom, it snaps. The same thing happens to the plates. The same thing happens to those tectonic plates. When they move along a fault, they push against one another, and it's like the two hands bending that stick. And then finally, when enough energy is stored, they slip, and that's like snapping that stick. Another way to think about this would be, imagine pushing a heavy table along a floor. If you have to push a heavy table, it would not move smoothly. If you're pushing a heavy table, that table's going to move bump, 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 like that, in little bursts of movement. Well, the slippage of tectonic plates is the same way. Tectonic plates do not move against each other slowly. They move a little bit at a time. So you'll have a long period of no movement and earthquake. No movement, earthquake. No movement, earthquake. That's why in places like California and Japan, they say the longer you go with no earthquake, the worse the next earthquake's going to be. Because if you go a long period of time with no earthquake, with no slippage, there's a lot of energy stored up. It's like the two hands bending that ruler or bending that stick further and further and further, so that when it does break, it releases much more energy. Next, slide 8, aftershocks and foreshocks. This is like, a foreshock, a small earthquake that precedes a major quake. And an aftershock is a small earthquake that follows the main earthquake. You could imagine here, like, if Godzilla came through your town. Before he came to your house, you would hear his footsteps coming. Boom, 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 boom. They would get louder and louder. Those are like the foreshocks that come before an earthquake. And then he passes, he destroys your house, and then that's the earthquake, crash. He walks on, and you hear boom, 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 as he walks away. Those would be the aftershocks, hearing his footsteps moving away. So foreshocks and aftershocks. Remember Godzilla's footprints. So how do we measure earthquakes? Well, we do that with a tool called a seismograph, which we are going to see which you can see on slide 10. We have a seismograph, an instrument that records earthquakes, and a seismogram, which is the actual chart that records the ground motion made by the seismograph. So the seismograph is the machine, and the seismogram is the thing that it writes. That chart is the seismogram. Kirk, I think we've lost our connection. Okay, let's roll. All right, and so there is an illustration of these two on. Whoa. Okay. And as I mentioned, there is an illustration of a seismograph and a seismogram on slide 14. You can see what's happening there. We have a pen attached to a weight, which is hinged to allow movement. That metal box, the support, will move along with the earth, but that weight, which is hanging from a string, will not move. So the box and the paper roll will move. The pen stays still and records the motion. On the next slide, we see a seismogram. One thing I want you to notice about this are those foreshocks. The first P wave and the first S wave. Now let's take a closer look at that to learn what exactly is a P wave and what is an S wave. On the next slide, 8.2, measuring earthquakes with earthquake waves. Our body waves can be either P or S waves, as we saw on the previous slide. Our P waves, you can remember P because P stands for push and pull. Those are the two things that P waves do. They push and pull on the earth. So they compress and expand in the direction of the wave. It's like if you take a slinky and shake it back and forth like this, or take a spring and just shake it back and forth like this. The kind of wave you're going to get. What scientists call a longitudinal wave. So the particles move in the direction of the wave. These types of waves travel through solids, liquids, and gases, and they are the fastest of the waves. This is an important point. Remember that the P waves are the fastest. That's important, and we're going to see why that's important in a few slides. Next, the other type of wave, our S wave. These are the seismic waves. You can remember S stands for seismic, it can stand for shake, and it can stand for slow. So that's easy to remember. S waves, seismic waves, they shake. They're not longitudinal waves like a slinky. They're more like if you take a rope and create a wave, or take a whip and make a wave. They're like the waves in the ocean, what we call transverse waves. So the particles do not move in the direction of the wave, they move up and down at right angles to the direction of the wave. A seismograph, okay, so remember these are slower, but particles are moving at right angles to the direction of the wave, and they are slower. Oh. All right. On the next slide, you can see an illustration of these. On the top, we see those P waves. Remember, the pushing and the pulling waves. And you can see in that picture in the top left that those P waves are like the waves in a spring. And on the top right, you can see what would happen when a P wave hits a road. You can see all those power lines have been snapped because the waves have pushed and pulled those power lines, so they've been pulled apart till the lines have snapped. Going down in the middle of the picture, in the middle left, you see that S wave, the shaking wave. It's like a wave on a rope where particles move at right angles. So if the wave moves this way, the particles are moving up and down like this. They are not moving in the direction of the wave. And that's what creates those waves that almost like hills. They look like hills. The last type of wave, that wave on the bottom with the circles moving like this, that's more like the waves that we see in water. In a wave of in a wave in the ocean, that's how the water molecules are moving. That's how the particles are moving in a circular motion. If you ever look at a boat out at sea that's in a wave, you can see it's moving. It moves kind of like this in a circle. It doesn't move straight up and down. All right, moving on. So remember, our P waves, pushing and pulling, and they are the faster waves. The S waves are the shaking waves, and they are slower. And understanding the difference between these two waves is what helps us to determine earthquake distance. Look on the next slide, locating an earthquake. The first point, earthquake distance. The epicenter is located using the difference in the arrival between the P and the S wave recordings, which are related to distance. You can think about this like lightning and thunder. I remember when I was a little kid, my mom always taught me that when you see a flash of lightning, you can start counting until you hear the thunder, because you see the lightning and then you hear the thunder. So you can start counting, and for every second, that's about 350 meters. So if you see a flash of lightning and then you count 1, 2, 3, and then boom, you hear the thunder, you can think, okay, 3 seconds, 350 plus 350, 700 plus 350, 1050. So that lightning strike is about 1,000 meters away. Just as we can do this with lightning and thunder, scientists can do the same thing with the P wave and the S wave. We understand the speed of both of these waves, so by counting the distance, by counting the time between the two waves, we can calculate the distance. There's a good picture of this on the next slide. We see locating an earthquake. We have a map of the world. We see a globe on the right, and then there on the left we can see a graph telling us showing the travel time and the distance. You can see that S wave has a steeper line, and that P wave has a more shallow line because it moves much faster. So we've got that distance of about 4,000 kilometers. Notice the P wave, the lower line, travels there in about 7 minutes. But that S wave, because it's slower, it travels there in about 12 minutes. So there's a distance there of about 5 minutes. By using this graph, we can tell, okay, a 5-minute difference between P wave to S wave means the earthquake is about 4,000 kilometers away. And by doing this from several different stations, we can find the exact epicenter of the earthquake. You can see what they've done here in that globe on the right. They calculated the distance from Montreal they calculated the distance from Paris and then the distance from Sao Paulo. They found it was 8,400 kilometers from Montreal, so they drew that first thick red line. 6,700 kilometers from Paris, so they drew the second line. And then, 5,500 kilometers from Sao Paulo, so they drew the third line, and that gives us 1 point on the Earth that is the epicenter, where those three lines meet. Moving on, measuring earthquakes. Historically, scientists have used two different types of measurements, intensity and magnitude. The most common of these is the Richter scale. The Richter scale is based on the amplitude of the largest seismic wave. Remember, we looked at that seismogram and the seismograph earlier. We saw that that pen is moving back and forth on the paper. So when they look at that seismogram, they take the largest wave, the biggest wave, and they use that to measure the intensity of the earthquake. The next point, each unit of Richter magnitude equates to a roughly 32-fold energy increase. So that means that an earthquake with a magnitude of 7 is 32 times stronger than an earthquake with a magnitude of 6. And an earthquake with a magnitude of 8 is 32 times stronger than a magnitude 7. And so a category 9 is 32 times stronger than a category 8. So you might wonder, why do they do this? The reason is that earthquakes have a very wide range of magnitude. So if we were going to start with a category 1 earthquake, by the time we got to 2, we would have to use the number 32 if we were just measuring the size of the wave. If we're just measuring the amplitude, we'd have to go to 32. Then what we call a category 3 would have to be 1,024. What we call category 4 would be 32,000 something. Then a category 5 would be over 1 million. Category 6 would be over 32 million. Category 7 would be over 100 million. So think how silly it would be for scientists to say, okay, this was a category 1,700,000 earthquake. This was a category 32 earthquake. This was a category 32,600,000 earthquake. It would be so confusing. No one would understand what they were talking about. So we use a 32 base counting system. So we can just go from 1 to 10. The other way to do it is momentum magnitude. We derive this from the amount of displacement that occurs along the fault zone. We saw earlier in all of those pictures where roads have been shifted or those fields had been moved. When we measure momentum magnitude, we look at how much, we measure the magnitude by how much movement, not by the amplitude. Moment magnitude is the most widely used measurement because it is the only magnitude that estimates the energy released. And this is what we use to measure very large earthquakes. Here you can see on the next page that table tells us we have moment magnitude on the left, we have a description in the middle, and the estimated number per year on the right side. So you can see a moment magnitude less than 2. there are about 600,000 of these earthquakes every year. That means there's about 15 or 1600 of them every day. So you can see the Earth's tectonic plates are constantly moving a little bit at a time. These tiny earthquakes occur about 15 or 1600 every day. But of course we don't feel them because they're so weak. We go down the chart there till we get to the bottom. Look at the very bottom. 8.0 and above. These are great earthquakes that destroy communities near the epicenter. Yeah, a Category 8 earthquake can destroy a city. Remember that earthquake that hit Japan last year was about a Category 9, I think. Maybe like an 8.9 or a 9. Remember, we are on a base 32 system. So that earthquake, that Category 9, was 30 times stronger than an 8.0. So it was a tremendous earthquake that hit Japan last year. Also notice in the last column the estimated number per year. Look, a Category 3 to 3.9, we get about 100,000. Category 4 to 4.9, we get about 13,000. That's about 1/10. Notice the next one, Category 5 to 5.9, 1,400. Again, 1/10. 6 to 6.9, again, about a tenth. And again, 7 to 7.9, we're down to 12. 8 and above, we're down to 0 to 1 every year. If we keep going with this pattern, as you can imagine, a Category 9 earthquake would only hit about once every 10 years. So you can understand that earthquake that hit Japan was an exceptionally, not only very, very strong, but very, very unusual. The kind of earthquake that only hits the Earth once every 10 years or so. On the next page, we can see a list of notable earthquakes. This chart is rather small, but I want you to notice a couple of things about this. Notice how many of those earthquakes are in California in the United States. 1906, 1971, 1985, 1994. That was a very famous earthquake when I was growing up. The San Francisco Northridge quake. Also notice how many of them are in Japan. 1923, the 1995 Kobe earthquake, and then of course the earthquake last year that hit the country. That's because, also notice Chichi, Taiwan. That's because very close to Japan. That's because all of these areas are on the edge of that Pacific plate. And it's, remember what we learned when we learned about plate tectonics. That Pacific plate is very, very active. It's constantly moving around. So that's what causes so many earthquakes in those different regions around the quake. You have a transverse fault in California, for instance. Up in Alaska, it's a subduction zone. It's also a subduction zone down in Chile, where you can see several earthquakes. So yeah, notice just how many of those earthquakes are around the Pacific. We actually call that area the Ring of Fire because of all the earthquakes that happen around the edge of that plate. Next, seismic vibrations. The damage to building and other structures from earthquake waves depends on several factors. These factors include the intensity and duration, the nature of the material, and the design of the structure. On the next slide, you can see an example of earthquake damage. That building's just sunk. Next, slide 23, building design. Several factors that determine structural damage: the intensity of the earthquake, the nature of the material, the design of the structure. So a lot of these areas that are on the Ring of Fire that get a lot of earthquakes, they have to have very strict laws about the buildings that are made there, because they have to have very strong buildings that can survive in an earthquake. A good example is Taipei 101. Remember, down in Taiwan. When it was built, it was the tallest building in the world. But Taiwan is an area that gets a lot of earthquakes. So building such a tall building in a place with a lot of earthquakes seems very dangerous. So they had to make a lot of earthquake proofing. They had to dig a very deep foundation. They had to make a lot of reinforcement. They had to make it a very, very strong building that could withstand an earthquake. Another thing they have in Taipei 101 is a giant weight at the top. And that weight is on these giant hydraulic arms that can push the weight back and forth. So if the building starts to tilt this way, the arms will actually push the weight the other way and put the building straight again. It's called a mass damper, and they use that in buildings in earthquake zones to keep them straight, keep them from falling over. One effect of seismic vibration on the next slide, liquefaction. When saturated material turns to liquid, underground objects may float to the surface. You can see that on the next slide. That whole building there just sank into the ground. It looks like the Titanic sinking in the ocean, because the ground has just been turned into liquid. It's gone from a solid state to a liquid state, and the building sank into it. On the next slide, still with 8.3, the destruction of earthquakes, tsunamis. We all heard this word so many times with the earthquake that hit Japan last year. Tsunami is a giant tidal wave triggered by an earthquake. A slab of the ocean floor is displaced vertically along a fault. So the vibration of an earthquake sets an underwater landslide. It's actually the Japanese word for seismic sea wave. You can see an illustration of that on the next slide. Down there in the lower left-hand corner of the picture, there's that displacement, the movement on the fault line, which creates a transverse wave through the water, and then that transverse wave travels to the land where it crashes and causes a lot of devastation. And that was what caused so much of the trouble when the earthquake hit Japan. There was actually more damage caused by the tsunami than by the earthquake. The earthquake shook everything, but in Japan everything is built to withstand earthquakes. So that didn't do much. The damage came when the damage was caused when the tsunami hit, and that's what crashed into buildings, swept away homes, swept away cars, and killed a lot of people as well. So the tsunami can be more destructive than the earthquake itself. Of course, here in Thailand, we all know that it was about 8 years ago that the tsunami hit down in Phuket in southern Thailand, as well as Indonesia and Burma from the Indian Ocean quake. We remember it caused a lot of devastation down there in Phuket. And yeah, it caused the again, the same situation. The tsunami caused more damage than the earthquake itself. On the next page, we see a tsunami warning system. Large earthquakes are reported from seismic stations. Although tsunamis travel quickly, there is time to evacuate. One of the reasons that we can evacuate for a tsunami is that tsunamis can do a lot of damage, but they only do damage within a few hundred meters. As long as everyone moves a kilometer or so away from the sea, there's no danger in a tsunami. That's why warning systems are so important, because if people are standing close to the ocean, they will be killed. But if they move back, they'll be okay. That's why. So tsunami warning systems are very important to prevent the danger, prevent the loss of life from a tsunami. Some other dangers from earthquakes: landslides. We saw a few of these in our lesson on soil. Obviously, when those plates move and there's shaking from an earthquake, we can get those collapses. The greatest damage to structures is from landslides and ground subsidence. Yeah. We saw a lot of good pictures in our last lesson, landslides. And also fire. In the San Francisco earthquake of 1906, most of the destruction was caused by fires that started when gas and electrical lines were cut. Remember, we saw that picture of a longitudinal wave earlier in the presentation. I believe that was on, what, slide 5? But remember, I believe that was slide 12. When we learned about those P waves, which are like a spring or a slinky, and the land moves back and forth in the direction of the wave, and we saw how that can cause power lines to snap. It could cause gas lines to break and rupture. When that happens, you can have short circuits, down power lines, broken, leaking gas. All of that can cause fires. So that's another big damage from earthquake. Another big danger from earthquakes. A major danger. Major danger. On the next slide, we see a really nasty looking damage from a landslide. On the next slide, predicting earthquakes. It's very, very difficult. It's nearly impossible for us to predict an earthquake. Like I said, we can have warning systems for tsunamis, but as far as predicting earthquakes, we don't know when they're going to strike. Short-range prediction has not been successful. Scientists don't understand enough about earthquakes to make long-term predictions. The seismic gap is an area along a fault where there has not been any earthquake activity for a long period of time. Remember what I said earlier in the presentation when we talked about how the pressure builds up and all of that elastic potential energy breaks out at once. So the longer we go with no earthquake, the worse, the more powerful the earthquake is going to be. So the longer the seismic gap, the more powerful of an earthquake we get. The layers of the Earth. We know that the Earth's interior consists of 3 major zones: the crust, the mantle, and the core. There's a good picture of this on slide, well, I don't know what the slide numbers are. Alright, we'll cut this. If you go to slide 41, I think you should take a look at slide 41 during this part of the lesson. Just stay there. And on slide 41, you can see a diagram of the Earth with a section of the Earth cut away, allowing you to see the different layers in the Earth. Starting at the outside and moving in. The outermost layer is the lithosphere, also known as the crust. This is like the skin of an apple. Compared to the rest of the Earth, it's very, very thin. This is where we get all of our different rocks, our igneous rock, our metamorphic rocks. Most of them are made here in the lithosphere. That's the solid rock. These are the plates that are moving around. As we move down into the upper mantle, the next layer of the upper mantle is the asthenosphere. Now remember, we learned about this in our last lesson. That's the layer of liquid rock. That's that layer of, like, yeah, sort of liquid rock. The lower. So the plates of the lithosphere actually sort of float and drift around on that sea of liquid rock in the asthenosphere, that weak liquid rock. As we go down further from the upper mantle, the asthenosphere, down into the lower mantle, we get that's made of the same type of stuff, but it's solid rock. Oh, there we go. That's where we get solid rock, down there in the lower mantle. As we move down into the next level, the outer core, that light yellow area of the outer core, that's where we're going to find heavier metals like iron and nickel. The reason for this is because in its early days, when the Earth was very, very hot, all of that rock was liquid. It was hot, molten, liquid rock. So the heavier elements like iron and nickel were able to sink to the bottom. And then after they sank to the bottom of the Earth, into the center of the Earth, over millions of years, the Earth cooled, and that lower mantle, that orange area, became solid rock once again, or became solid rock. So now all of those metals, the iron and the nickel, are down there in the center of the Earth. And then at the very center, that little yellow circle, that's the inner core. And this is also iron and nickel, but there the pressure is so great that it's actually solid. Even though it's very, very hot, the iron and the nickel cannot melt. It's actually, there's too much pressure. It doesn't have the room to expand and melt into liquid. So even though it's hotter, it's white hot iron, but it's still solid. So the best way to remember that is that as we go down, we go from liquid rock to solid rock, liquid metal, solid metal. So that upper mantle, liquid rock, lower mantle, solid rock, outer core, liquid rock, outer core, liquid metal, inner core, solid metal. That's the basic composition of Earth, but as I mentioned, this is a theory. We do not know this. As I mentioned earlier in the presentation, we actually know more about other galaxies than we know about the inside of the Earth. So let's move on. Here we are on, well, tell you what, let's move back for a little bit. let's go back to slide 32. Um, Keeping this picture in mind, but we're going to go back to 32. Our outer layer is the crust. That's that thin, rocky layer. It varies in thickness. It's about 7 kilometers deep in ocean regions. In continental crust, it's up to 40 kilometers or even 70 in areas of mountains. The next slide, you can see on 33 the way seismic waves travel through the earth. Well, oh, wait, here we go. Oh, sorry. All right, it's next, 35. Let's take a closer look at the crust, the oceanic crust. That's basaltic composition. Remember, basaltic composition. Basalt is an igneous rock, so that oceanic crust is going to be a lot more igneous rock than the continental crust. That makes sense. Remember what we learned about the mid-Atlantic range, how those two plates are moving apart, making the Atlantic Ocean wider. And it's that hot liquid magma, the igneous rock, coming up from the inside the earth and replacing that older rock. So you can see it makes sense that near that fault line the rock is going to be newer, and it's going to be more igneous rock and less metamorphic rock. So in that oceanic crust we have more basalt, more igneous rock. Alright. Next, slide 36, we move down to the mantle. Remember, the upper mantle is the igneous rock peridot. Remember that upper mantle, also known as the asthenosphere, that's that liquid rock. As we move down, slide 37, you see the core. That's a lot of nickel and iron. Very high density. All right. Slide 38, we're looking again up at the top, the lithosphere and the asthenosphere. We've talked about those. The lithosphere, that's the crust. The upper mantle, it's rigid, it's solid. Those are those solid plates moving around. The asthenosphere, that's that liquid rock. It's weaker, it can be deformed. And down there in the lower mantle, the rocks are more rigid, more solid. And again, like I mentioned, the inner core behaves like a solid, the outer core is like liquid. You can see all of that illustrated on slide 41. Remember, the upper mantle is like liquid rock, the lower mantle, solid rock, outer core, liquid metal, inner core, solid metal. The next thing I want to talk about, on slide 42, look down at the bottom of the slide, this shadow zone. This is part of the theory, part of the information, the evidence that we have for this theory about how the Earth is made up inside. If you look on slide 43, you can notice that when we have an earthquake, when we find the epicenter, we can see there are certain areas of the Earth around 105 degrees to 140 degrees around the globe where we don't see any P waves. We always see this with earthquakes. There are P waves all around the Earth, and then to 105 degrees they stop. Then at 140 degrees they start up again. That's why we think that we have that outer core, that metal area, that's actually deflecting and bending the waves. So you can see there in that picture that dark brown area between 100 and 140 with the dotted lines. Those are the waves that we might expect to see, but we're not seeing them because they're being bent around the Earth. They're being bent around the core. Again, it's important to remember that a lot of this is speculation. We don't really know a whole lot about the inside of the Earth, but we are always learning more. Scientists are always coming up with clever ways to make inferences about what's inside the Earth. But for now, it remains a great scientific mystery. But it's one that is worth investigating further. All right, thanks for tuning in, and I will see you next time.